So this is the last lecture in the series of lectures we've been talking about forcing of vibration. Okay, so we've talked about a whole succession of different ways that the system can be forced, by which we mean it's different ways it can be shaken. Okay, so up to now we haven't really talked about arbitrary signals or random signals, so this is what we're going to do in this lecture. Okay, so this kind of covers an approach to signals that don't fit into sine wave type of categories. So not all our forcing signals are going to be sinusoidal, are they? Okay, and so in fact, you could argue that the majority of them won't be sinusoidal. Most kind of forcings that happen in the real world will be some other type of signal. Okay? So we're going to have a framework by which we can deal with those types of signals. Okay, so we can have things which aren't periodic at all, which I think we mentioned at the very beginning. So these are things like impulses and shocks. Okay, so when something experiences a sudden impulse or a shock loading like an impact, something like that, then that's a non-sinusoidal type of forcing. So we can have things that are periodic but aren't sine waves. Okay, so something that's an arbitrary periodic signal is just something that repeats like on a specific time period. Okay, so there's lots of examples of those things that aren't sine waves. So you can have things that are square waves, for example. You can have triangle waves, sawteeth, things like that. Okay, and you can have things which look like distorted sine waves but aren't actually sine waves. Okay, so you can have a whole series of arbitrary periodic responses, but they're not sine waves. Okay, and then of course probably the most relevant one for a lot of applications is random vibration. And for most things that we deal with, or a lot of things that we deal with, even if it's not quite a random excitation, we would often assume a random excitation. So for example, for a vehicle traveling through an airflow, we might know that actually there's some structure to the vibration, but for all intents and purposes it would look quite close to random. Okay, so we might use random excitation or random forcing. So when we look at these types of signals, the frequency domain becomes very important. Okay, so as you all know from your maths lectures in some time in the past, that we can go from the time domain to the frequency domain using Fourier transform. Okay, we can also do a transformation from one domain to another using the Laplace transform. Okay, so if you're a control engineer, you'll find that you use the Laplace transform. You can make an equivalence between Laplace and Fourier if you put S equals to I omega. Okay, so we'll always use, in vibration theory, we always use Fourier. And we tend to write this down as a pair. Okay, so we're going to write down a pair. Okay, so little f of t is, if it's in the time domain, it's a small f, and if it's in the frequency domain, it's large f. Okay, so that's the usual convention. And then in brackets, I've put the t and the omega to show you, to emphasize whether it's in the time domain or the frequency domain. Okay. And usually what happens is, in some of what your maths classes, you'll have been made to do some Fourier transforms, okay, where you do the forward transform and the inverse transform. You go from one domain to the other. Okay. Luckily now we have computers, okay, and we have something called the fast Fourier transform. Okay, so we have an algorithm which is actually not the same as, it's equivalent to doing this, but it's not the same as this, and it makes life a lot easier. So now in MATLAB, if you want to, you can do Fourier transforms very easily. And in fact, we've even gone beyond that, and later at the end of this lecture we'll see something called the power spectral density, which is an even more advanced version. Okay, so in MATLAB you just need to do PSD brackets, you put like a vector in of the time signal, and it will give you a nice frequency domain representation. Okay, so we don't need to solve these by hand, but this is the concept of where it comes from. So we've got a forcing signal f of t, and it goes into the frequency domain, it becomes big F of omega. We'd have an equivalent response as well. In fact, it's arbitrary, so any signal, we're dealing with vibration problems where we shake something with signal f of t, and we see that the mass responds with signal x of t. But of course, these could be any signals, couldn't they? So this is a concept that you'll have seen in control engineering, if you've done control engineering. So now this is entirely in the frequency domain. Okay, so control engineers like to work with these types of relationships between what they call the input and the output. Okay, so they think of a signal that I'm saying is a forcing signal. They say that's an input, so you're shaking something. Okay, and then the output would be the response, the x. Okay, and they tend to draw a diagram like this. Okay, so in this kind of scenario, we put an input into this box f, and we get an output of x, and then the magic bit g is how the signals are related. Okay, so that's like it's usually called the transfer function. So if you remember when we did all of these previous ones for our force signal, if we just take our relationship that we derived previously, we have g of omega, something like this. Okay. is I put a force in. G of omega is like an operator now. Okay, so it operates on the thing that I'm putting in, and then I get an output out. And what's interesting is that despite the fact that we derived these expressions, this G expression, we derived it for a sine wave input and a sine wave output, it turns out it does a very good job of modeling it, the system response for any input and output. Okay, so electrical engineers think about this as a filter. Okay, so they say, well, essentially, if you derive it using sine waves, you get this characteristic of a filter with a resonant peak, okay, which is equivalent to our sort of dynamic amplification factor, and they say, well, that's the characteristic of the system. It doesn't matter what signal we put in, the filter just acts on the signal. It could be noise, could be anything, and then we'll get an output. Okay, so this is an alternative way of thinking about it. Of course, just to remind us, R is omega over omega n. So this is an interesting example. So piston-driven engines. How long do you think it's going to be before there's no piston-driven engines? So probably middle of this century, most cars won't have piston-driven engines, will they? Maybe lorries? I don't know. So in the beginning of the 20th century, of course, piston-driven engines were kind of revolutionary, weren't they? And now you can see that there's a future where they may not exist anymore. So I probably won't be teaching anymore after them, but somebody who's teaching this will have to think of another example, won't they? So piston-driven engines are a classic example where you get a non-sinusoidal response. So this is a frequency domain plot. This is just a schematic to show the key contributions in this frequency signal. Okay, so this is the beauty of the frequency domain plots. We've looked at some of these in the early lectures. Okay, you remember when we had the single sine wave looks like a single peak in the FFT plot, doesn't it? Okay, so this is an equivalent of an FFT plot. So what the Fourier transform or Fourier series analogy tells us is that every signal can be broken up into a series of sine wave contributions, doesn't it? So if I look in the frequency domain, I can see what are the contributions, what are the sine waves which build up that signal. Okay, so when people first made piston-driven engines, they kind of thought it would just be a sinusoidal type of behavior, but it turns out that it isn't quite sinusoidal, and you actually get quite significant harmonics at 2 times, 4 times, and 6 times the fundamental frequency. Okay, so in the early part of the 20th century, there was a lot of work on how to resolve that problem. So random forcing is probably the most important one for all aspects of engineering, aerospace engineering, automotive engineering as well. To deal with random forcing signals and responses, we need to kind of develop a few concepts first. Perhaps they're revision for most of you. So first is expected mean value. So that's written like this. It's capital E, square brackets, and then inside the square brackets is the signal you're taking the expected mean value of. So if we're taking the expected mean value of our forcing a signal f, and what it means is it's 1 over t, integral from 0 to big T f dt. So it's kind of what we'd think of as a time-based mean or average, isn't it? So if we've got a random signal like that, what we're doing is we're integrating over time until we get to a value big T, and then essentially we're taking an average over that time. So maybe that we get here. Okay, and quite often it's written as f over bar. Okay, the expected mean value. A related concept is the mean square value. So this is the same thing, but we take f squared first. Okay. So if we take f squared, then everything will be, it becomes positive. Okay, so everything is above 0, and then we're taking the mean based on the time evolution of that. Okay, so that's quite often again written as with an overbar. So f squared with an overbar. So the variance so as I'm sure you've seen from statistics, variance is normally written as sigma squared. Okay, and in this context it's f squared bar minus f bar squared gives you the variance of the signal. And if we know variance, then we take the square root to get standard deviation. So standard deviation is just sigma. So this is one of the most important things when we're doing this type of analysis, is whether the signal is stationary or not. Okay, so a stationary random signal is one where the expected mean value is 0. Okay, so if the signal is stationary, and this is true, then you can do a lot of analysis. Like I was just hinting, you can basically use the same analysis as sine waves in many regards. Okay, and use it on stationary signals. If it's non-stationary, then it's a more tough proposition. So non-stationary signals are things like earthquakes, for example, which tend to sort of shake the ground and then maybe end up, with the ground higher or lower than it started before at the beginning. stationary signals tend to be those which are oscillating randomly, but fluctuating around some mean. Okay, some value which averages out to 0 or close to 0. So the next concept is probability. Okay, so probability distribution first. So if we take some signal x of t, okay, so we can define an arbitrary x value, x1, okay, and then we can look for places where x1 the signal is less than x1. So these are the little time intervals where the signal drops below the x1 value. So delta t1, delta t2, and so on. We're just looking at those values. So then we can define a function p of x. Probability that x of t is less than x1. So again, we add that up over a time period and average it. And so we'll get a value for the probability distribution with relation to x1. And so the probability distribution for all points will look something like this. Whoops. If it doesn't fall off. So if we take an arbitrary point, what this is saying is if I move x1 from the left to the right, I'm including either all of the signal or none of the signal. So the probability distribution goes from 0 to 1. Okay, so if I bring x1 down and down and down, then eventually almost none of the signal is included. Okay, so that's a probability distribution of 0. And if I move it up and up and up and up, then I I include all of the signal, then I can asymptote to 1, don't I? Okay, so that's all this little expression is telling us. So this is related to a more well-known quantity which is called probability density. So to get density, what we tend to do is we think about a small delta x part of this system. So we'll draw the graph directly underneath. So how do we get this function? So this function is somewhat confusingly called little p of x. Okay, so this is small p of x. This one at the top is big P of x. So that's just the convention. I'm not trying to confuse you. So the top one is distribution. The bottom one's density. We'll write an expression down for it in a moment. Okay, so what is the density? So this is little px on the left is the limit as delta x goes to 0 of big P x plus delta x minus big P of x divided by delta x. So it's a derivative. So as we take that limit, it becomes a derivative of the distribution function, doesn't it? So that's the same as dpx by dx, where we're talking about big P on the right hand side again. On the diagram, what we have is P of x here. This is P of x plus delta x, isn't it? And this is distribution. And this bottom one is density. So just the last thing on this, the other way they're related, they're often written as being related like this. So this should be big P of x1 is integral minus infinity to x1 small p of x dx. So all of that gets us to the point where we can talk about common probability density functions for random signals. Okay, and what we're effectively doing is we're saying if our forcing function behaves like one of these common signals, probability density signals, then essentially our output behaves in the same way, and all we're doing is we're changing the amplitudes essentially of the input and output. Okay, so the one I'm sure you'll mostly have heard of is Gaussian probability density function. It's definitely the dominant one in all the vibration analysis that it gets done. It's a very, very useful function. If anybody doesn't know what a Gaussian probability distribution is, there's a very easy way to see it if you visit a historic building, isn't there? So if you go to some stone steps in a castle or a historic building, then the wear on the step is like that. Okay, and that's a Gaussian probability distribution upside down, isn't it? Because over thousands of years, as people stand on the step, the probability of standing in the middle is the highest, and the probability of standing on the edge is almost zero. Okay, so the stone on the step wears in that pattern. Okay, so it occurs all over the place in sort of physics, essentially. So let's draw a picture. So in this one, you'll notice that I deliberately drew the mean off center, okay? Because that's in general terms. Nearly always, the probability distribution will be centered around an even mean. Sorry, I haven't drawn it very well. It's supposed to be symmetrical. Okay, so it's supposed to be symmetric. So there's been a huge amount of work on Gaussian distributions, and people have come up with analytical functions which approximate this shape. Okay, so one that you can use is this one. Okay, so that's an analytical approximation of the shape. And a good sort of rule of thumb is that 68% of values lie within plus or minus sigma. This curve here, that was my step. You can ignore that. I was talking about a step, wasn't I? That was my sketch of a step, like a stone step in a historic building that lots of people have trodden on, and they've worn the middle of the step down. Okay, so it's like the upside down of a Gaussian distribution. But you can ignore it for all intents and purposes of the notes. Okay, so we're going to accept that our signals are Gaussian, so the inputs are going to be Gaussian, the outputs are going to be Gaussian. Not always. There are some other probability density functions that could be used, but we don't need to think about them really for our purposes. So we need just a small amount more before we get to our final representation, which is the power spectral density. So we need to introduce something called the autocorrelation function. Okay, so this is usually written like this. Okay, so it's usually written as R, capital R, of a specific time value tau, and it's going to be equal to an expected mean value. So this looks a bit strange, doesn't it? What is this? What on earth is this saying? So what this is saying is we've got some random signal x, and what we're going to do is we're going to use tau as a time parameter, okay, which can sort of roam up and down our signal x. Okay, and what it's going to do is it's going to go through all the different other time points and compare it to the time point we're at now. Okay, then it's going to normalize it by dividing by sigma squared. And it's going to take the expected mean value of those two things multiplied together. So it's like you're normalizing it in several ways, aren't you? So you're normalizing the signal with the mean first. So x minus its mean, x of t plus tau minus its mean. Multiply those together, take the expected value, and divide by sigma squared. Yeah, mu. Sorry, that I haven't written down what that is. That's the mean. Yeah, it probably helps if I actually write down what it is, to help you understand. So this looks a bit strange, but it's been built up by statisticians essentially, or signal processing theory. And so it's a measure of the content of the signal comparing with itself, if you like. Okay, so you can actually do this with comparing two different signals. Okay, so you can take a correlation function between two different signals. And then you're saying, how much does this signal, look, it's similar to this other signal. So let's say we had x and y. Okay, we could take those two signals, we could try and compare them, couldn't we? Okay, autocorrelation means compare with itself. So this is saying, how much does the signal compare with itself if I look at a bit here, and then I take a bit over further along or in the previous part of the segment. Okay, so it kind of tells you how much the signal is varying amongst itself as it evolves. So then we get to the power spectral density function. And that's the Fourier transform of R. So you can see it's got S subscript XX. So that's because we've got this autocorrelation where we're comparing X with itself. If we had XY there, it would be a cross correlation between signals X and signals Y. Okay, so if you see S with an XY as a subscript, that's also a power spectrum, but it's built on the fact that instead of an autocorrelation, it's got a cross correlation. And what does it look like? Let's just write a note about XX. XX means so paraspectral density looks, when you plot one, it looks like this. So if you take some signal and you plot it, you get these very clear peaks. Okay, so it depends what we're looking at, but the peaks are the dominant frequencies in the response signal. Okay, so if we had a very, very flat signal, okay, so typically, in theory, a white noise signal that had frequencies up to infinity would have a very, very flat kind of signal. Okay, because it would contain content in every single frequency value. Okay, and if you arranged it so that the amplitudes were fairly constant, you should get a flat signal. But what you tend to get is a very peaked signal with vibration problems, and so those are the dominant components in the signal. And so normally if we're interested in resonances, things like that, then the peaks will correspond to some of the resonances in the system. And as I say, now you've got MATLAB and other pieces of code that can work these things out for you. It's very easy to take some data, put it into the power spectral density function, and then immediately see what the dominant sort of components are of your signal. Okay, thanks for that, guys. That's all for today.